So when you think about a solar system, there's a kind of standard picture in your head, right?
Absolutely, the classic layout.
The classic layout. You've got the small, rocky planets huddled up close to the star.
And then the huge gas giants are way out in the cheap seats, out in the cold. It just, it makes intuitive sense.
It does. But today we're doing a deep dive on a system that seems to be, well, completely ignoring that logic.
It's not just ignoring it, it feels like it's actively shredding the textbook.
We're looking at LHS 1903. It's a red dwarf system, about 116 light years from us, and the sources are calling it an inside-out system.
Which is a perfect way to put it. It completely inverts the density pattern we'd expect to see.
I saw one analogy that just clicked for me instantly. They called it a double-stuffed Oreo.
Huh, I like that.
Yeah, a rocky planet, then two gassy planets, and then another rocky planet on the very outside.
And it's that outer cookie, that last planet, that is really giving astronomers a headache.
So let's break down that lineup from the TESS and CHEOPS data. First up, closest to the star is LHS 1903b.
Right, that's a super-Earth.
Yeah.
But the key thing is its density. It's really, really dense.
Which makes sense because it's getting blasted, right? Any atmosphere is just
It's
gone.
long gone, stripped away eons ago, leaving just that heavy, rocky core. So far, so normal.
Okay, then we get to the filling of the Oreo. Planets C and D.
Yeah.
These are the mini-Neptunes.
Exactly. These formed in that sweet spot. They had enough material and were in the right place to just scoop up these huge envelopes of hydrogen and helium.
The physics still holds up, but then you get to the outlier, Planet E.
Yeah, the weird one.
It's the furthest out, it's in the cold, it should be a gas giant.
By all rights, yes. But the data shows it's a naked super-Earth, about 1.7 times the radius of our planet, but with no thick, puffy atmosphere. It's just rock.
Finding a rocky world out there is like, what, finding a perfectly baked potato in a deep freezer?
That's a great way to think about it. Standard theory just says you build giants out there, so what happened?
Did it, crash into something and lose its gas? Or migrate from somewhere else?
That was the first thought. Maybe it's a really chaotic system. But a dense, dry rock out there suggests a totally different kind of structural logic.
A whole new set of rules.
A different rule book. And, speaking of optimizing structures and building intelligent systems.
Oh, I think I see where you're going with this.
It's actually a pretty good lead-in for our sponsor, Embersilk. If you're looking to streamline your own systems, we're talking AI training, automation, complex software integrations, they offer the solutions.
It's all about finding where agents can make the biggest impact for your business or even just for your personal projects.
Exactly. You should check them out at embersilk.com.
Okay, so back to our naked planet. If it wasn't a crash, how does a rock form in gas giant territory?
The leading theory is something they're calling gas-depleted sequential formation.
Sequential, so one after another.
Precisely. And the key variable isn't just location, it's time.
Ah, so it's a race against the clock.
It is. Think of the protoplanetary disk, all that gas and dust, as a buffet that's about to close. The inner planets, C and D, they got there early while the buffet was fully stocked with gas.
So they got to bulk up and become mini-Neptunes.
They gorged themselves. But Planet E, it was late to the party.
Way too late.
By the time it started forming, the star's solar winds had already blown most of the gas away. The buffet was closed.
So it's a late bloomer that could only form from the leftovers, the solids.
Just the dust and rock that was left behind. There was simply no gas for it to grab.
But how can we be sure they didn't all form and then just, swap places? A big migration event.
They tested for that. They ran these N-body simulations, basically fast-forwarding the system's gravity for millions of years.
Yeah.
And it stayed rock steady. If there had been some violent migration or giant impact, the whole system would have flown apart in the simulation. That stability is the smoking gun.
Wow. So the planets are essentially a recording of the disk's history.
That's a beautiful way to put it. Their composition tells you when they arrived, not just where.
And what this means for, the bigger picture. This is actually really optimistic news, isn't it?
It's fantastic news. LHS 1903 is an M-dwarf. That's the most common type of star in our galaxy.
So if this inside-out architecture can happen there.
It could be happening all over the place. We've been looking for rocky worlds mostly near their stars. This tells us they could be hiding in the outer reaches of systems, too.
It just broadens the search area immensely. Nature has a much bigger playbook than we've been giving it credit for.
Our solar system is just one model. A classic, for sure. But LHS 1903 shows the universe loves to improvise.
It really makes you wonder, doesn't it? What other impossible configurations are out there just hiding in the data, waiting for us to figure out the right questions to ask?
That's the exciting part. We're just getting started.
A perfect thought to end on. If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.